this is where we start I'll call it the difficult part of the session, but also the audience participation part of the session. So I would like to invite the co-chair of the three committees that are here to come here and sit at the table. So John, Eric, and Colleen. And I'm going to put up a slide where Jeroen has tried to summarize. Let's see if I find it. Is this one here, Jeroen? Okay, so this is actually going to be really tiny, but this is not going to work. So let's do this, and I'm going to try to slide it. Okay, so, well, we're going to move from the scientific themes to what is needed, and it's going to be out pretty much the entire time we're going to have this discussion, so you're going to have time to read through it. So the first thing, to kickstart this discussion, I would like to first, we took the scientific themes from the 2009 Grand Challenge document, and then the way they were then extracted to be represented in the SAGE proposal. And you find them here for sort of a summary. But what we would like to focus today during this discussion is to hear from you and to discuss, again, whether, for example, these are we have heard, common approaches and opportunities coming out to approach these scientific themes. And you see them here summarized. We try to summarize them all and what is needed to resolve these scientific themes. And the first thing that I'd like to ask you is, do you think these are all the things that we need? All these are the opportunities that, the speakers have mentioned. Are these the opportunities? Are these all the opportunities? Or is this a full list? Or do we have other opportunities that are not mentioned here? And I'm going to read them for those of you that probably can't read them in the back. So, for example, many of the speakers have mentioned develop high-resolution images of the Earth interior, fault zones, and melt pathways. Improve imaging inversion methods with uncertainty quantification, joint inversions of active and passive source data, continental ocean transitions arrays, time-dependent seismic imaging, very broad recording, for example, Earth system and interdisciplinary approaches, handling of high data volumes, and high-performance computing. Is this all we need? Are those only the opportunities? Or do we have, this is actually the moment where we're going to discuss these things. Because if you look at the schedule for this meetings, we're going to then move to facilities and data. But during this plenary session today, we would like to focus on the science. And this is this is the first time, we're going to discuss that together, with the recompetition of 2018 in mind. And so this is where we're going to meet together and discuss our scientific goals. John, Jeroen is going to move around, and I'm going to grab the other.
Can you hear me? Wow. Sorry. I think we had some really great presentations this morning so far that very clearly enunciated some fascinating scientific problems. I do think the list, however, is somewhat incomplete, in that there's a portion of the Earth that seismologists image regularly that is not well represented by what was said this morning, and that's the lithosphere. We saw in the first session the driving forces from beneath. We saw in the second session how the lithosphere is deforming actively, but only at the relatively short time scale of seismicity and active tectonics. And we saw in the third one how the lithosphere is interacting with the cryosphere, the place where we live, the cryosphere, the atmosphere, the oceans where we live. I think these are all fascinating and important topics. But in between those, there's a lithosphere that contains a 4 billion year history of the evolution of the continents that has, I'm going to use the words that are used in the mantle, the thermochemical, internal dynamics, and volatile distribution that over 4 billion years makes the continents on which we live. And that's not listed by the set of science problems that we're talking about this morning. I think it's a critical part of what seismologists contribute in collaboration with geologists as to how this planet works and how continents work.
So then to address that question, how do we, what are the approaches that are needed to address those questions?
Well, from an approaches perspective, I think it's a very similar list, but it's a different scale. It's a scale of kilometers to tens of kilometers as opposed to a scale of hundreds of kilometers. I think that's the critical difference. I think the scale is in common with the active processes that create earthquake hazards and induce seismicity in volcanoes. So certainly there's a lot in common there. The tools and the approaches that are needed are in common. But in terms of the scientific goals, it's a different set of scientific goals. So I don't think that significantly changes the approaches and opportunities, but I think it changes the scientific justifications, the scientific targets that we're aiming for.
Okay. And as we have these discussions, I think we should keep an eye on also the questions of whether we have those facilities, whether we need to modify those facilities that are existing in the core programs of IRIS, and if we need to modify those facilities, how we want to modify them.
Well, I'll say something about that. I think at certain points in the community, we have established some reliable, well-supported workflow and software solutions. I guess SAC and GMT come to mind that really are, again, well-supported, robust. A lot of people use them, so there's critical mass. I still think we're lacking a lot of those capabilities across the community. And there's, of course, a tremendous amount of inefficiency as we and more frequently our grad students end up reinventing the wheel. And I think this problem is going to become much more acute with enormous data sets that we're envisioning in terms of full wave field seismology, as well as we go with more ambitious experiments on smaller scales. So I really think that's something that the data services and the whole IRIS community more broadly, and actually the geophysical community more broadly, really needs to try to get on top of. If you look at the models that are successful, they're not typically these general, broad, let's put together a workshop and write a white paper kinds of things. They really involve finding incentives for individuals who will go out and actually pursue the development and promulgation of these software tools on sort of a career scale. And I think we really need to think about finding niches in our community for that type of individual to thrive.
Hello. One observational approach that isn't on there that I think touches on a lot of the different scales is looking at magnetotelluric data. And that's currently being distributed to some degree through IRIS. And that's relevant on the fault zone scales. It's relevant on the continental or oceanic lithosphere scales. So I think good integration and kind of growth of how that's brought into the seismology community is probably a wise thing going forward.
Am I next? Okay. I want to expand a little bit, or you could have expanded one of those bullets a lot, which is this state about interdisciplinary approaches. There are about 5 sub-bullets under that, but the one I wanted to comment most upon is we really need a more close union, I think, between geodynamic modeling and seismology to advance the field beyond where we are. We sort of do our own little thing, make the little tomography models or whatever, and then the modelers do their own thing, and then you kind of try to throw them together in the end, right? But I think a real challenge for us as a community is to make ourselves more integrated in that sense, because both things are poorer for not working together more effectively. So that's my...
Yeah, thank Brandon for bringing up the magnetotellurics. It's good to hear a seismologist speaking up on this. It's more than just magnetotellurics. It's more general electromagnetic methods. And I think IRIS has played a role in that I'm going to talk about after lunch. That I hope they stay involved and continue this work. And then just sort of a related issue on approaches and opportunities. And I think it's also related to what Gary was just talking about. Joint inversions of active and passive source data is far too limited in terms of what you should be thinking about, what we should be thinking about in terms of joint inversion. We should be thinking about data assimilation, connecting our data sets to the geodynamic models, and obviously also we should be doing joint inversions of seismic data and EM and gravity and everything, and more integrating things with the physical model, petrophysical models and things like that.
Touch on something that Rick was talking about in terms of the lithosphere. EarthScope is producing this phenomenal data set that gives us really an astonishing view, I think, starting primarily mid-crustal levels and then deep into the mantle. What we're missing at some level is the linkage between that and the anthroposphere, the upper crust and the near surface. And we think, well, a lot of that's really industry concern, and actually a lot of it isn't. The industry is very focused on particular target areas, but there's no synoptic view on that scale. And I think, we're going to have to get our heads around what's the practicality of collecting truly high-resolution data on a truly epic scale like that, and what kind of new technologies do we need to develop that may not be in the existing facility.
Yeah, I want to follow on from that. That imaging at those shallower levels also has a lot of applications for hazards. I'm working in Charleston, South Carolina, where on one hand we have a very deep sedimentary column, but we have these very interesting impedance contrast in the top 100 meters that I'm finding out have a lot of topography on them. I was just discussing with someone what effect that has on site response during earthquakes for areas, along the east coast of the U.S. We have one thing I'm learning over the years is we have very different styles of impedance contrast, different from the West. Our geology is different. We actually do need to image those shallower, and shallow doesn't mean that the geotechnical engineers do top 30 meters. It might be the top kilometer, right? And we have to know what that structure is, what the impedance contrast is, to more accurately predict ground motion during earthquakes, whether it's the earthquakes in Virginia, earthquakes in South Carolina, maybe up in Boston, other areas in the east where we do have seismicity and a history of large seismicity. We need to do that everywhere, not just a lot of favorite places we've been doing it. And having facilities and being able to do that fairly efficiently was a very useful thing to do.
I'll throw out something from up here if there's not a question.
Yeah, no, go ahead.
I guess just to be a little controversial, there's a long list, and a lot of these things are all good, but to me, two things stand out that we heard this morning, and one is, having a lot of instruments to look at the earthquake rupture itself. That's a very poorly understood problem, and there's a lot of room to make improvements. And the other is to do the seafloor monitoring and get a good look at the subduction zone. To me, those two stand out from the ideas we've heard.
So if there is nothing else, I would like to instead ask you if, as a community, you think that the core programs we have are appropriate to attack these problems. Should we develop them? Should we change them?
Well,
Who's that? Oh,
the one thing that comes to mind is we are not really open to multidisciplinary things, and especially if we want to open up the oceans. I'm thinking of the floats that I'm developing. There, the next generation of floats will service the biologists. They want to do census of whales. They will serve the meteorologists because they can now measure rainfall, the quantity of rainfall from the kilohertz noise that the rain gives. The oceanographers have historically deployed thousands of floats to measure salinity and temperature in the oceans. And so our programs are monodisciplinary, and I wonder what the options are for IRIS to be more open to collaborations with sciences beyond geophysics.
I'm glad that Steve, I think it was, made the comment about hazards. I mean, IRIS has historically been, of course, a lot of us do work related to hazards in some aspects of our careers, but as a consortium, IRIS has been historically circumspect, let's say, in terms of really embracing the issue of seismological hazards as a core type of activity. And I think that, well, as everyone knows, I mean, this is not a problem that is going away. In fact, it's growing globally, and it's going to be of increasing interest probably if trends continue in the U.S. funding community. I think we really have to think about ways that IRIS and partners, USGS obviously, and others can constructively and I think more assertively embrace the really important problems in earthquake hazards and hazards related even to the built environment as well.
How do people feel about that? Should we move into hazard?
I'll just add a little bit on the hazards point. I think it seems like it's really important on a number of levels, especially there were some conversations about, partnering with other agencies. There's a little bit of attention, of course, that, we want to maintain, the motivation, the contributions from the sort of basic science in terms of source processes, propagation, and what happens at the base of a structure. But I do think it seems like there's very little on here with respect to hazards, and one opportunity seems to be the induced seismicity problem, to just get out there to provide opportunities to make better observations in these kind of almost laboratory-like situations where, and it goes really to crustal or even upper crustal spatial scales. I think the other part of this would be earthquake early warning and the ability to assess sort of the evolving source processes during the event and then explore ways to efficiently provide information to communities out in front of the propagating wave field. So those have really good science problems associated with them, but they're also super practical and be worth probably mentioning or having IRIS have some structure that relates to them.
Okay, so let me ask you this question. So we heard 6 talks this morning, and they discussed the science challenges, and they presented, where the science is going in the future. Then, do you think that to go in that directions, we have the facilities that are needed? Yes or no? Let's start with simple questions. Okay, John shakes his head. And he made he made a provocative statement, opening this, and, okay. And if we don't, what is needed, of course?
One of the things that came up a number of times was deployments of large numbers of sensors. There are a lot of reasons we want to do that, but I think for our facilities to do that, maybe a more sustained, a sustained and a more of a partnership with industry, seismology might be a productive avenue in that as we get to deploying really large numbers of sensors, we may never drive that field or be dominant in that field of creating technology. We could be a significant partner in it and an innovative one, but that may always be driven by industrial forces, and it'd be good to be aligned with them if we want to get into deploying that technology. And so that might make a little bit of a different programmatic approach than to, say, deploying broadband seismometers that have 100-second corner periods. And outside of this community, there aren't a lot of people who drive that technology. So the programmatic approach might need to be different with these very large element styles of observation.
So one of the things I was struck by with Eric's talk was his comment at the end that we need to put a lot more instruments on volcanoes, and that's where I am working professionally. And the thing that struck me was we tried that at St. Helens, and I'm not sure if that's entirely an accurate statement or not, but for the St. Helens 2004-2008 eruption, we were working very hard to put instruments as close as we could to the crater. And despite that, we still have some fairly fundamental basic questions about where the earthquakes were located, even though we were putting stations within a couple hundred meters. And what that really pointed to was that there's incredible complexity in the shallow surface that is a part and parcel of figuring out that problem. You have to address both of those in something that's better than what we did, a larger version of N than what we did. And also, we were not using the right instruments. And I don't think the right instruments are available to the community right now. We need instruments that record things well, and you don't cry when they disappear, because they will. And sort of following on that, one of the opportunities, not just in volcanoes, but in other areas where things are ephemeral, is the sort of whole question of how do you capture the ephemeral occurrence when it's the data that you need is the most important data is when it's actually happening, and you don't necessarily know where they're going to happen. So response is all part of this, and response requires planning, requires integrating with the folks that are going to be involved in the response, who are going to be managing it. And just thinking about the forest fire up here, the folks that are managing that, their focus is very much on the here and now, what they already have done. They have plans in place. And the cliche that emergency managers like to throw around is that a crisis is not the right time to be exchanging business cards, and that you really want to be in there ahead of time. And so as a community, one of the things that's needed that's not on this is integrating the seismologic questions, or geophysical or geologic questions with an event-driven kind of scenario. What kinds of questions do we need to be addressing when the next eruption happens, when the next induced seismicity crisis happens, and who are the folks that we need to be integrating with now so that we're ready, much readier to go, because it's something that where 24 hours makes a big difference.
With response to Beatrice's question, I think we also want to consider, are we making use of the facilities that we already have? And two things come to mind that we may be able to do better, and one is integration with other facilities, in particular geodetic monitoring. Are we really maximally using together what we can do seismologically and geodetically? And I think I would argue that we could do a whole lot better integrating the two than with the facilities that we already have. There are data that are gravely underutilized. Another example of that is the data from offshore in the Cascadia experiment, and merging those with the onshore, the whole concept of onshore, offshore. I think we still have yet to get to the stage where we can call that truly integrated onshore, offshore monitoring. So think we also need to ask, are we really making the, and is there a way to make better use of the facilities we already have?
So I think when Bix raises the question of are the facilities that we have adequate to do what we want to do, I'm thinking about it in particular in the context of the onshore-offshore problem. And having worked in this both as a scientist and being involved in the OBS program that NSF funds and IRIS now operates, I think one of the challenges that we face, obviously, is that this is a very expensive proposition. I think it's very clear if you look at the Grand Challenges document, you know, many of those, 6, 7 of those, really point to observations in the oceans as really being a key component to move forward in those problems. A coupled part of that, I think that we saw in some of the talks today, is that other types of observations can also be really critical. And I'm thinking in particular of seafloor geodesy, seafloor electromagnetics. We talked a little bit, a comment earlier on integrating with that. And it strikes me that, you know, the difficulty in moving into the oceans is really in large way driven by cost, and it's also driven by trying to figure out how to better integrate these disparate activities, pre-existing activities in some sense, into a framework that we've already really developed well. And sort of combining those two things and being able to reach outside the seismological community to sort of help address the cost problem potentially, to help address provide a greater scientific motivation in a broader part of the earth science community to justify large costs for these kinds of endeavors, but also at the same time, you know, utilize the strength that we have as a seismological community. We've invested a lot in the facilities that we have, in the infrastructure we have. I think we're widely seen as leaders in the earth science community in terms of building these kinds of facilities, and yet we, I think for good reason, have been really focused on the seismology problem. We were self-identified with that. We didn't want to be stepping on other groups' toes. We need to figure out how to sort of get beyond that a little bit, I think, in terms of solving some of these problems and being able to build facilities that utilize our expertise, are coming from our core, but at the same time are bringing in some of the communities in a very collaborative and community-driven way to help get more resources and to establish these large infrastructure that I think we're going to need to move into the oceans and really do these big problems across the globe.
I'm a big advocate of a large number of stations. As other people have mentioned, I'll be talking about that, the large stake this afternoon that I invite you to participate in. I'm also a big advocate of rapid deployments and the ability to have a ramp that we can respond to events, and we simply do not have that in the U.S. today. It hasn't changed in 50 years. The third thing that we need, and it's an order of magnitude improvement in spatial resolution that can be enabled by active sources. We're making great strides in improving what we can do with ambient noise, but that will never overcome the resolution that is available with active sources. And although there is a source facility built within the SAGE budget, it's a tiny one. I think we need to define what that is and develop that in order that we can actually do the imaging at the highest resolutions when we need that for the scientific problems that we're trying to address. So I would add sources to the missing facilities here.
And I will have to agree.
I just wanted to point out one thing about, we've been talking a lot about large N and using, you know, what we do as our bread and butter, like picking P waves and using that to understand things about earthquakes. When it comes to other newer ways of using seismology to understand certain systems, like we heard about the glacial problems, we heard about sediment flux. I think there's still some very fundamental issues that need to be figured out, that where we don't really need large N, where even just a couple single stations can give us useful data. And also, along with that, we need to improve some of the modeling of of those signals. So, for example, how does, well, one thing that I'll talk about later is how does water flow contribute to a seismological signal that we can measure, and can we make use of that signal to infer something about those systems? And so in some cases, maybe we don't need to be talking about super expensive large deployments.
One thing I think is definitely missing from your list here, and part of the facility that's problematic, we've heard several people talk about it, that what should be up there is something about cyber infrastructure, because we have historically the IRIS data management system, or whatever it's called, and the emphasis is on data delivery, and a lot of these problems are solvable by a more integrated system that somehow has the capability to make it easier to exchange models of different groups together. It's things about what Rick talked about a minute ago about being able to be better about processing the data, ask a question and be able to answer it in a finite length of time. So it's definitely a missing system that I would propose that DMS should become DCS, I guess. Actually, no, it's CS or whatever, Cyber Infrastructure System.
Hi, I think Team Aiken would be a better person to answer this one, but I know the team is involved in one of those building block proposals to build such a cyber infrastructure. So there is a big initiative within NSF, it's called EarthCube, and the idea is to build exactly such an infrastructure as is being discussed now. And I think IRIS is trying to play a role in it, which is hopeful.
I have, just coming back to the sensor, sort of the large N and sensors, I guess I'm not a network person, but one of the things I think of going forward is to kind of think beyond the sort of more traditional sort of big network design that is kind of maybe typically used, and think of it sort of N in numbers of sensors and M in things that are observed. So really thinking of these networks as these observation platforms that go beyond just the sort of motion of the ground surface, but other environmental sensing that's maybe able to integrate with the basic seismological observations, and then really give us this sort of multiple views on the processes that are of interest. And you know, that's a huge expertise from this community on the technical side is getting sensors into places and getting data off of them. So what more could be done to sort of broaden the observational capability?
One thing that I think might be a little overlooked is making our models actually comparable to each other, because even something as simple as a color scale can be completely different between two different models. I've found that with my research, I try to compare my attenuation tomography to someone else's attenuation tomography, and the scales are off, and I can't directly compare anything. And so maybe standardizing some of what we do would actually lead to being able to better compare with each other and better able to decide which models are correct, which ones aren't. So that might be something to think about a little more.
I'd like to sort of be a little bit cynical and suggest that we need to think very seriously about the relative proportion of our enthusiasm for large observational projects versus the amount of funding that is being provided to the analysis of these data sets, past, present, and future. I think it's very easy to convince people to build something. It's much more difficult at the moment to actually get new ideas for scientific workbenches or large inversion codes or all the kind of things that uses expensive programmers. any of those kind of endeavors, which are even smaller than the scale than what was discussed earlier today, sort of the $1 million scale as opposed to the $10, the $100 million scale, is very difficult to do right now, and I think is really holding us back. And in that context, I think we need to think about how much it's important to do these large scientific endeavors from the analysis perspective within the context of observational programs versus having the science that's associated with them funded, again, through the original individual PI programs, as Jim was describing the earlier struggle they'd gone through, because it's really hard to predict where the new analysis tools and the new discoveries are going to come from. And if we rely completely on these large consensus-driven documents, we're liable not to make the progress that we should be making.
I just wanted to speak up again in regard to how we employ our graduate students and the products they produce. I just feel like these students work very hard. They make data products. They do improvements to software, and then they go somewhere else, and all of that is sitting somewhere on a disk. And in most cases, never to be used again. So I just think some organization where students can be perhaps guided about how to improve certain software that could use improvement, how to use the data resources around, and we have our big DMC and so forth, but there's not a lot of interface there, and it all falls to the student and obviously their advisors, but I just don't think we're capturing all that good work in an efficient way.
Actually, I will follow up on that, capturing the good work, and put it in a broader context of education and public outreach. We are at a sort of unique point in time in our K-12 educational system where a large number of states around the country are adopting a single science set of standards, the next generation science standards. And actually, I see Hust Nolet on the side there. I remember a conversation we had going back decades about how wonderful it would be to have a capstone earth science course in high school to pull a student science education experience together. And it's finally happened. Actually, we have this now as part of the next generation science standards. It involves a year of complex integrated earth and space science education for all high school students, as well as a year at middle school. A dozen states have already adopted this, and there are 24 other states that are in the process of adopting it. So this creates a tremendous opportunity for us to get our science in forms that could be integrated into classrooms. And so really for the first time there is a call for, as well as a pipeline, to get our science into the educational experience of most Americans. But there is a need for our science to be in a format that can be used by middle school and particularly high school science programs. So I really put that challenge out for us to get our data. The new science standards are data and evidence driven, and so they, of course, using raw data is not something that will be always so easy for them. So data products are going to be more in line with what will be needed. But there's a tremendous opportunity for our community, because we are so organized, to really make advances in getting seismology and geophysics into the awareness of all Americans, or most at least.
I just had one topic that I haven't heard is that thinking about laboratory experiments where they start earthquakes and watch them happen from earthquake nucleation to super shear. Last summer, Jay Feinberg said, "Can you model the waveforms in our experiment?" And I said, "What's your sample rate?" And he said, 500,000 samples per second. Of course, it's not a long experiment, but the idea that if the barrier in my mind was if that data were, there are metadata, they know exactly where their source and receivers are. If that data were at IRIS and we could just grab it, that's one barrier that would allow that step toward, they're making earthquakes, these papers, you see them in Science, they're remarkable examples of the processes we're talking about. No new data, but they've invested massive costs in designing those 1 second experiments. So that's one idea where it seems like the expertise of IRIS could make it easier to others to look. And I don't really know what happens to those waveforms. We just see kind of really pretty snapshots in science papers, but it'd be neat to have those archived.
Hi, I'd like to make a comment just on the duration of recording. A lot of the experiments we do tend to have, 1 year to 2 year kinds of durations. And there's a number of problems you'd like to look at where you want to see the time variability in processes such as slow tremor and slip, volcanoes, glaciers. And I think something to think about also is when we're designing the next big things, how long do we want to be recording? And I think there are opportunities out there where we might be wanting to look at much longer recording intervals than we're looking at now.
I think something that's been missing from maybe the list and also this conversation is we need to think about how our science directly relates to society. And we have that. I mean, some people have touched on that here. But how does your mantle tomography, what is that going to do for society? And I'm not choosing that because I don't think it's a valuable science, but I think we need to critically think about that in terms of not only our facilities, but the projects and the endeavors that we move our science towards, and also in making our science something that, as, I'm sorry I don't know your name in the back, but that we can disseminate to the entire American population. And that we have, I guess, we're fortunate that our science actually is not something as abstract, maybe, as other sciences. And I think that when we fundamentally ask ourselves what our questions are in terms of moving our science forward, I think that that is a critical question. And we often, I think, move away from that. And it's easy to do when we're dealing with theoretical models and other science that we tend to focus on. I just think that we need to think about that question every time we ask ourselves, where are we moving towards? What is important? How can I relate this back to society, and how does it impact the overall world?
Yeah, I just thought I should bring up something for kind of the younger, I think I'm speaking for the younger generation of seismologists that are coming up now. But there seems to be this huge computer language barrier. A lot of us are using these grandfather codes from forever that have been duct taped together. And I think it'd be good for maybe something that IRIS could do. Since we don't get funded or we don't get our PhDs for translating codes into languages that we can modify easier, and they just end up being a patchwork of C and Fortran and MATLAB that do what we want, but they're not optimized very well. And I think maybe that could be a position that IRIS could hold. And I think it's not so much for the scientific merit, but important for scientific progress in the younger generations that are coming up.
I'd like to get back on to, and it actually feeds off of the last comment a little bit, but some previous ones. We're kind of bemoaning the lack of realizing the full potential of integration across all of these different data types, geodesy, various seismic data types, MT, et cetera, and there's sort of an NSF and institutional policy issue here, because very rarely is there any one institution that has broad expertise across all of these domains. So that means intrinsically, if you're going to train the next generation of researchers who truly can understand how to do things like joint inversion across all of these different methods, you're going to have collaboration across institutions. You're going to, in essence, have to share grad students between institutions. And there really isn't a good mechanism for that. Years ago, we tried writing an IGERT aimed at EarthScope for trying to tackle part of that. I don't know if IGERT's the right mechanism, but I don't think we're ever going to cross this barrier until we train the students from the get-go to think in those terms. Otherwise, we're going to just keep reproducing ourselves in our own disciplines.
Following up on one of the comments about student education, I think specifically we have high data volumes and high performance computing up there, and some targeted training on handling large volumes of data and using these high performance computing resources specifically from an earth science perspective could be very valuable. I think at the last EarthScope meeting there was some discussion in the SIG about how earth scientists tend to use these HPC resources a little differently than other scientists who use them. And I think it would be really helpful to get an earth science specific perspective on there. There's a lot of good information and training in general about how to use this high performance and high data volumes, but we have our own specific needs, and it would be really valuable to have something specific to our science to address that. Anything else? Okay, well, we're almost at the end of our session, and obviously everybody's thinking about lunch. As we go through the rest of the meeting, I will encourage you to think about these things, about our science goals and our facilities and whether we're ready for it. And discuss and think and reach out and use this as an opportunity. This is probably going to be the only opportunity we have to come together before we start the process toward our next proposal writing. And so this is really, like Anne said, a very special IRIS annual meeting. So have a good meeting and think about these themes, and thank you for the speakers, by the way, that talked today, and thank you for the chairs of the sections and for the chairs of the committees, and have a good lunch.